This video will be on constraint optimization, and I'll start by doing an example. So here we have optimize f of xy equals x squared y subject to x squared plus y squared equals 1. Now, what this is saying is to find the local extremas, so maximum and minimum points for this multivariable function such that we only take points that live on this equation. Okay, so the maximum we find and the minimum we find should satisfy this, and these aren't generally the same maximum and minimum that we could get from just using this with no constraint. Okay, now if you forget about this problem and just think of this surface as any multivariable function in two variables, f of x, y, and look at this constraint, which is a cylinder, then optimizing f of xy subject with this cylinder, or it's actually, if we look from here, just a curve, a circle, is us trying to find the maximum point and the minimum point, which are these two. These two are the maximum and the minimum points for this surface that satisfy this equation. Okay? So now how can we approach a problem like this? The constraint is clearly just that the points must lie on the equation. So what we can do is, if we have f of xy equals x squared y, and here we have x squared plus y squared equals 1, we can think of this as x squared equals 1 minus y squared, and then we can use this in this function. So we'll get h of y equals 1 minus y squared multiplied by y. So all that I did is plug this into this multivariable function, and this is what we get. By doing this, we guarantee that whatever the input is, it's like gonna go back to the constraint for whatever y and get the corresponding x. So the points always live on this equation. Okay, now we'll just go on by differentiating this and equating that to 0. So first, this is going to be y minus y cubed. If we differentiate this, we get dh over dy equals 1 minus 3y squared, and that's going to be 0. So if we solve this, we have 1 equals 3y squared, which is y squared equals third, and y equals positive or negative 1 over root 3. Okay, to get the corresponding x, we go back to this equation. So we have x squared equals 1 minus y squared. So we can get rid of this and make this positive or negative like this. And then if we plug y, so at y equals 1 over root 3, we will have 1 minus 1/3, which is going to be positive or negative root 6 over 3. Okay, just doing it on the calculator, and I missed positive or negative here. So then we can try at y equals negative 1 over root 3, and we'll also get the same answer, which is positive or negative root 6 over 3. And this says that we've got 4 points that can act as either a maximum or a minimum or a saddle point that live on this curve. Okay, we can write these down. So for y equals 1 over root 3, we had root 6 over 3. We also had, for the same, okay, so sorry for this mess, I'll try to clean things up. Okay, for 1 over root 3, you also had negative root 6 over 3. And then for negative 1 over root 3, it's just the same. So these are going to be our our points that can act as either a maximum or a minimum or a saddle point that live on this curve, okay? And that's all I wanted to show for this video, so thank you so much.